Good evening, everyone, and welcome to the live session, seventh live session for the course Deep Learning for Computer Vision, conducted by Professor Vineet N. Balasubramanian. So, up until last week, we've discussed about various aspects of computer vision techniques. I remember last week we were talking about object detection and segmentation, which was a slightly different task than what was done up until the week before that. So, up till week 5, we focused on typically a image classification task. That was the main, like a implicit or a default task for whatever algorithms we were learning. But last week, we discussed about two different tasks called object detection, where the goal was given a particular input image, the model should not just identify what class the particular object falls into, but it should also identify what are the bounding boxes across each object present in the image. When I say bounding boxes, it is nothing but a imagine it to be like drawing a rectangular box across a particular object in an image. So that is what is called as a bounding box. And then we've also discussed something about segmentation. In particular, there are two types of segmentation. One is called the semantic segmentation, and the other is called the instance segmentation. In semantic segmentation, the goal was basically to identify or classify every pixel into a particular class. So classification is classifying the overall image, which consists of thousands of pixels, then classifying that overall image into one class. Segmentation is like classifying each pixel into one class. So if you visualized the output of segmentation, it would look nothing but like kind of like a masks, colorful masks, and each colored mask will be a different object present in the image. Instance segmentation is another extension to semantic segmentation, where you also give separate color coded masks for each instance of an object. So, for example, if there are two dogs in an image, semantic segmentation would give both the dogs red color mask. But instance segmentation would give dog one blue color mask, dog two green color mask. So it separates even the different instances of the same object present. And if I remember clearly, we also discussed about the UNet algorithm, which is a very powerful and popular algorithm for segmentation tasks. And we also, in the code walkthrough, we discussed about how to build a UNet architecture, and we saw the entire training pipe. So coming to today's week, that is the week 7. So I hope you all watched the lectures, and it was related to different types of modeling of the modeling algorithms called sequence to sequence modeling algorithms. So typically, till now, the input has always been a static sample. So typically, image, right? An image is one element, but that is not the only type of data out there. Now, if you see your typical text data, right? A sentence consists of multiple words. Each word can be like a image, like a single element. But usually, typically, you don't give one word to the model. You give an entire sentence so that it makes sense of what the sentence is. So in that case, you basically try to give each word as like a you know input will be consisting of a sequence of words. So we call it sequence to sequence modeling. Yeah, I think there's a question. Yes, please go ahead, Olivia. You can ask a question. Uh, you can unmute and ask a question if you have a question, Olivia.
Okay, sir, actually, I wanted to ask that, sir, yeah, I want to actually build a project which requires this object detection model.
Okay, so maybe let's discuss that at towards the end of the class because object detection we already covered last week, and also like if it's a personal project, I'll prefer we can discuss it towards the end of the session.
Okay, okay, sure.
Yeah, thank you. Yeah. So yeah, if you have any questions, please feel free to post it in the chat, or you can unmute since it's a small number of students available. So yeah, coming back to the sequence to sequence modeling. So I was saying like typically an image consists of one static image, whereas sequence to sequence models, if we draw it out, it will look. Let's differentiate. So up till now we saw like one image. Let's call it I. And let's say we have a model. So we send this model image I as an input to the model, and we expect some output. The output could be the different tasks based on the task. Basically, it could be like a classification, it could be like an object detection, it could be like a semantic segmentation or instance segmentation. Now, coming to sequence model, the input is no longer one static image. Instead, it will be a bunch of, let's call it, um, sequence 1, sequence 2, sequence 3. Not called sequence 1, let's call element 1, element 2, element 3. And this entire is like one input sample. It doesn't have to be 3 also. It can be anything, n number basically. Now this entire one input sample will go as an input to the model M, and then we get the output. Again, here also output, it can be multiple things. We will see in today's um, session what are the different things, but output doesn't have to be like a one type of an output. There are different types of output, and based on the different output, just like how we had classification, detection, segmentation, here also we'll have different names based on the type of output we have. So I hope this difference is clear between how we are transitioning from your standard image or a static one input sample to a sequence to sequence modeling, or having a sequence as an input as to the model. If there are any doubts, please let me know. I'll move ahead for now. So typically these live sessions, I think at this point everyone is aware of it, but let me reiterate. So we usually divide this live session into two parts. The first part of the live session basically has few numerical MCQ fill in the blank type of questions, and which are related to the concepts taught in that week. In the second half of the live session, we basically have code walkthroughs, which will help you solve your coding assignments. So today's first question is very simple. It basically says that you have two different sets, set A and set B. So set A is a type of modeling we do typically in sequence to sequence modeling, like many to one, many to many. It means like, think of it like input to output. Many input elements to one output element, or the second is many to many. It means many input elements to many output elements. So it like that. So set A has different sequence to sequence modeling type. Set B has the type of applications, and you have to basically match which particular application belongs to what type of a modeling. So maybe I'll pause for a few seconds. You can read the question and try to answer it by posting your answers in the chat. Any guesses doesn't have to be correct. Just keep it as interactive or try to attempt as many problems. Even if it's wrong, it's fine. Uh, can you please expand on what is B, like which particular option is B? Many to one is sentiment and classification, true. I think you meant to say many to many as machine translation. Yes. So I think pretty much all of you got it. So one to many is music generation, many to one is sentiment classification, many to many is machine translation. So maybe let's try to, I know you all got it, but maybe let's quickly recap this and we can go ahead to the second question. So, what is music generation? Why is it called one to many? So, for example, if I have any sequence, I'm not talking what model for now, you can any sequence model, I'm calling it SM. So, typically, music generation, what is the application? You want to generate an entire song, let's say, right? And typically a song consists of like 3 minutes, 5 minutes, 10 minutes in length. So your output will not be like one particular second. It will consist of like 3 minutes worth of seconds. So each minute is like 60 seconds. So it will be around 180 seconds. So if you assume your model can output at one instance 1 second, so it has to output like that 180 different seconds worth music. So this is basically, and your input will be one. Let's say maybe you're just saying like a start tag. That could be your one input. Or you can anyways just give like any trigger basically. Then you can quickly convert this into one to many problem. And with that start tag or some trigger, you're generating an entire song of 180 seconds. Some people can argue why just a start? Can we also give like an entire text prompt? In today's time, we have like an entire text prompt, right? With all your chat GPT and everything. And then this can be thought of also as a many to many out sequence modeling. So in today's time, when you're doing text to music generation, yes, you can convert that text to music as many to many. But in a typical music generation sense, it is typically one to many because there's no text involved. Okay. Now coming to many to one uh, task, which is sentiment classification. So sentiment classification, typically, what does it say? It is trying to identify the sentiment, or in other words, trying to identify the emotions present in a given sentence. The sentence doesn't necessarily have to be one line. It can be a paragraph, it can be a book for that reason. Any review, also movie review, music review, it could be anything. So trying to classify what is the type of emotion, is it positive emotion or a positive sentiment, or a negative emotion, negative sentiment? That is the that is the task of the sentiment classification. So let's see how that it is modeled. So typically, let's say movie reviews, right? A movie reviews will be a bunch of sentences, like a paragraph. Now that entire paragraph will go as an input to your sequence model. The output will just be either a positive class or a negative class. So it's a single output, either positive or negative. You can again complicate it, but since the standard sentiment classification is positive or negative, it's a many to one modeling. Now comes many to many, which is machine translation. Everyone is aware about the task of typical translation, language translation. Forget about anything to do with AI. In general, in real world also, there are many translators available who translate one particular language to another language, like English to French, English to Chinese, Chinese to Hindi, etc. So typically, when you want to model this in with the help of your AI algorithms, which is nothing but your sequence modeling algorithms. So what we have as an input, your input, let's say, is in English. Like I have a dog, and we want to convert or translate this into say another language. Let's say French for that reason. So you send this as an input to your model, sequence model, and again the sequence model output will not be one or two sentence. It will be a bunch of different sentences. Like I actually don't know French, but let's say there are some X, Y, Z, A, B, C words. Okay. So these are all a bunch of different words, French words that basically translates to I have a dog. So here you can see the input is many words in a sequence, and the output is also many words in a sequence. So that is what is a many to many modeling. Now let's go to the second question. So now let's go to till now I've talked about sequence models, but I didn't mention what are these models. So the typical name for any sequence to sequence modeling, which is a neural network, if the sequence to sequence neural network model is RNNs. So RNNs stand for recurrent neural networks. But that doesn't mean that all sequence to sequence models are RNNs. Only the neural network family of architectures which do sequence to sequence models, those are called as RNNs. There are other non-neural network architectures also which can do sequence to sequence models. So remember that distinction. It's not like all sequence to sequence models are called RNNs. It's only neural network family of algorithms. Okay, so typically RNNs is the most standard family in neural networks which do sequence to sequence model. Now, there are some problems with RNNs, which again was discussed in the course recorded lectures also. So maybe try to answer out of these five options, which are the problems associated with your standard traditional RNNs. And you can post your answers in the chat, and we can discuss one each option after like a few minutes of time. Yes, I think as Rajesh sir has pointed out, it's all of the above. So yeah, I think people have correctly guessed it. So maybe let's discuss how does RNN look like, and then we can go back to the options itself. So we saw right now input is not a static image. So let me put the inputs at the bottom. Let's say I have an input and I'm calling it I am a human. Okay. Now each of this input will go into a hidden state. Okay. So it's basically not directly go to an hidden state. You can think of it like this will be a weight matrix. You multiply your input, which is your x, with the weight matrix, you get the good output. Typical like your MLP, right? Your MLP also at the top I'm drawing, right? So MLP also has these nodes, right? So each edge is nothing but a weight. You multiply input with weight and you get the activation out or intermediate outputs. The H is nothing but the same node over here in MLP like that. Here also it is there. The only difference is now H is dependent. Like for each H in the entire sequence, each word's H corresponding H will be dependent on the previous H also. So what do I mean by that? Let's say this is H0. Now let's make this second as H1. Again, it will be some other W. Sorry, the W's will be shared. And then we have another H2 W. Mm, I can make this H3 W. And all of these will also have connections like this. So what is the idea over here? Why are we having these connections? Like I said, this is all sequence to sequence model, which basically says that uh, previous words depend on if you're modeling some word, right? Like for example, I am a human. The human over here and the over here, they're related with each other. It's not like distant. These are different samples. Each of them is connected with other words in that sentence. All of them together make sense. Individual words, while it might make sense, but in that the context is lost. Like I individually is a different meaning. When you're coming to a sentence, I, that context will be referring to that particular sentence. So to make sense of your entire sentence, you have to give each of the word in such a way that they depend on each other. So that is what this H to H dependency is. Now, output of each of the H's, so it depends on your modeling type. It could either be one output, like just go all of them go to Y0, or each of them, let's say many to many now in this case. So each of them will output something Y1, Y2, Y3. Okay. Now, this all corresponds to just one particular sequence corresponding output. This is not like three, four different input samples output. This is just one input samples, one corresponding output, which again has four elements. So today we will see in the code walkthrough a very similar problem, this one-to-one, which we call character level model. We will see in the code walkthrough how we can do this exact thing. So this is how typically your RNN algorithms are. Now, in your standard RNN algorithms, there's nothing else. No particular gates like in what is it, forget gate or memory state. Nothing is there. It's very simple. Just like how MLP does your many to many connections, RNNs also have a many to many connections. Just that there is also dependency between the H's. That is it. Now, based on this understanding, let's go and look at the options. The first one says it is prone to vanishing or exploding gradients problem. So what is the problem itself? So as the name suggests, gradients. Okay, what are the gradients? Gradients are nothing but these are feedback signals coming from your loss function, which will tell how good or bad your current prediction is, or your current parameters which you have, right? How good or bad they are compared to the actual what we want, optimal solution. So the gradients are important cues, but since these networks typically are very big in size, when the gradients start back propagating from the last layer to the starting layer, somewhere in between, they either become very small, and when they start becoming very small, small numbers multiplied by smaller numbers become even smaller, and at some point, for some layers, the gradients will become completely zero. And when the gradients you're getting as zero, those layers will think that whatever predictions they are making is correct, or whatever weights they have, those are correct. But that is not the case. In fact, the what the weights they are is wrong. It's just that they're getting a zero gradient, which is kind of like biasing or fooling them into believing that they're actually solving the problem. So that is the vanishing gradient problem. Exploding gradient is the opposite. When your gradients are very huge and big numbers multiplied with each other again cause another big number, and typically again learning stops, because beyond a point there's no point of having that big gradients, because the weights are just here and they're running, it goes to infinite also sometimes. So RNN, since they have no limitations as to how to control these feedback from the gradients, they typically are very prone to such type of vanishing or exploding gradients, typically in like bigger and bigger networks, because there's no control mechanism. There's just simple connections made with them. Okay. Now, next problem is problems in dealing with long-term dependencies. So this typically you deal when you have you know a two-page document, 20 pages book, even for that reason, even like a 10 paragraphs, whatever you have, that is all long-term uh, contextual problems. So in today's time, you all must be familiar with the word context, right, in the terms of these LLMs. So everyone talks about, oh, what is the context window? My LLM has certain context window, chat gpt has certain context window, etc. Context window is nothing but what is typically the input sample, not input sample. The sequence, like I said, consists of words, right? So typically, how many words can go at once as an input to the model? You can think of it as a context size. We don't usually send words; we send something called as tokens. But for now, you don't worry about that. You can think of it like words. So if I'm sending a paragraph, if I'm sending a 10 paragraphs, typically that consists of like 500 to 600 words. So at a time, the context that I'm giving to the model is 600 words. And typically these LLMs have very huge context sizes, and that means it can read bigger and bigger documents. And that is the reason why, even if you give like a research paper to it, it can read the entire research paper and still answer correctly whatever questions you're asking it. Whereas a typical RNNs have this problem. They can't do it again. Why? Looking at the algorithm. This nothing else. This is a very simple connections. If you think about it as a computational graph, a simple connections. There is no way for it to understand which is important. Let's say it read three paragraphs. In that three paragraphs, it just no one ever told it. Okay, in these three paragraphs, these parts are the important parts, or these are the subjects that they're talking about in the paragraphs, or this is the context that is being set till now in this paragraph. There's no such control at all. We just left the algorithm to its own. You learn from its own, and typically it's hard when you have like bigger and bigger documents. So when you, in those cases, the simple RNNs, they fail to answer your question correctly. So that is called as long-term dependency issue, which typically RNNs suffer. And yes, another problem is processing data sequentially, which is just what I said. Typically, again, sequential data, when you start processing, there'll be a lot of issues like computational efficiency, forgetting issues, and all those things. And RNNs are very prone to this. And that is where the actual advantage comes with attentions. I think probably your week 8 touches upon the attentions. We can discuss about that later. So, RNNs typically process your data one after the other. What do I mean by one after the other? Sorry. So it first processes I, then am, then A, and human. So computations happen one first process H0, then H1, then H2, and H3. Attentions, on the other hand, do everything parallelly. We will see about it next week, but just remember this is a very important difference between your standard RNNs, that includes all your typical RNNs like LSTM, GRUs, anything. All of them do your data processing sequentially, like one after the other. Attentions have everything done parallelly. How do they do it parallelly? We can see it in the next session. So, yeah, given all of these options, all of them are correct. All of them are the problems of RNNs, and that is the correct answer. Now let's go to the question 3. So this is based on LSTM. Now LSTM was one particular type of an RNN which is more efficient because RNNs, like I said, is a very simple graph. LSTMs made it smarter by having certain mechanisms, or which we call it gates. And these are the three different gates that are in a typical LSTM: forget gate, input gate, output gate. And these are the equations on how to actually calculate these: forget gate, input gate, output gate. And there are some other C bar and C, which is like context or memory state kind of an information that's happening. So based on your understanding of from the course recordings, what does each of these gates do? What is the functionality of each of the gates? There are three options. Try to match each of them. Let me pause for a few seconds and try to answer this problem. No, that is not correct. One, the options which you, the answer which you give is not correct. Just think carefully. Like, go with the intuitive meaning. What does forget gate should ideally do intuition wise? It's just try to see exactly the intuition and how they can connect with the answers. Mm, Now it is correct. It is one. Sorry, it is one C, two B, and three. So this is how your typical RNN functions. So maybe let me draw a very broad diagram. I'll explain actual mechanisms in the next questions. What are the actual equations and all? But for now, let me give you a very broad overview. So we typically saw that H previously in RNN, right? In LSTM, we don't have a simple H. We call it the cell, or we call it LSTM cell, whatever you want to call it. Now, this LSTM cell first receives information from the previous time step, t minus 1. And inside these LSTM, there are three different mechanisms, functionalities, gates that happen. First is your forget gate. Then you have your input gate. So this input gate, like the name says, it takes the input also from your original, like this time steps input. Then you have your output. An output gate, like it says, it tells how much should the output um, of this particular LSTM cell will be sent to the next time step t plus. So the intuition is very simple. Forget gate basically gets the old information and tries to understand, okay, out of all these informations which I got from my previous times, how much is actually relevant for my current time step? How much of the information I keep in this particular time step? Input gate, it decides new information that is coming, which is that particular time step, along with the old information, and decides what should be the new information that should be stored in this cell. Now output then finally combines this old information, the previous time steps, this new information, and decides how much should it send to the next time step, t plus 1. So this is what typically your LSTM cell consists of. Now if you relate back to your document reading or document understanding task, what was it, like given like a paragraph or two paragraphs? Okay, so let's say at second paragraph's end, you're entering this particular LSTM which I drew. Now, what forget gate will do? Okay, up till two paragraphs, what is the irrelevant information that I don't need to use at this point? It'll forget, like maybe some random, objects like trees, bike, car, or grass, which might not be very relevant. Again, this depends completely on the problem. I'm just giving you an example. Something irrelevant information, it tries to forget. Now, at that particular time step, which is the start of the third paragraph, you're getting a word. Okay, in this case, not word, like few words, let's say. And now you want to know in these few words, how much of these few words should you keep, or should you keep all the few words, or are all of them important, few of them important, or some of them important, some kind of mechanism. Then finally, in the output, basically it says, okay, instead of sending everything two paragraphs plus this third paragraph starting words as an output. How much of a more extracted information do I send as an output to the next particular LSTM cell? So this is how typically your LSTM cell tries to model. So I hope that is clear. If there are any doubts, please let me know. And equations, of course, very important. I've skipped it right now because these are the same equations taken from the recorded lectures. So maybe let me quickly overview what are the different terms. So W's are your standard weight matrices. Each of the gates get their weight matrices. X's are your inputs. This sigma notation is your standard sigmoid function. B is the biases. H of t minus 1. This is like your previous information, hidden states information. U is another type of like contextual matrix that will basically, depending for each gate, tries to understand what all information it has to take from the previous thing. So think of it like a contextual. C and C bar is like your memory states. They both relate to that. And finally, your output, the HT is your current time steps hidden state and how much you want to send it to. Output will decide how much you want to send it next. Now let's go to question 4. Here we're talking about trying to differentiate between two different RNNs, popular RNNs. One is your LSTMs, other is your GRUs. So there are four different, you can say, dimensions on which you can differentiate between these two RNNs. So take your time, read all the dimension questions. Like these are like four different questions. Each question has one correct option. So try to answer, read the options and answer which of them is correct. Or let's just wait for others also to read and then we can discuss the answers. Okay. Let's discuss the. I hope you all were able to read the options. Yeah. So the correct answer is all B's. And let's look at the models itself, and then we go back and solve the questions. Okay. So this is how typically you have the three different sequence to sequence models apart from your attentions. Sorry. Yeah. So RNNs were the most simplest graph which we saw previously. Now it is the same thing what I drew. It is slightly drawn differently. You get the input X, take the your input, then your previous hidden state, you send it to the activation function, then you get your next how much to send to the next HT and your output also. That's it. No control whatsoever. All you do is matrix multiplication and one non-linearity. Could be whatever. In this case, it is tan H. Now let's come to LSTMs. Like I said, LSTMs are popular. It was one of the popular algorithms when it came out, and they did propose three different types of gates. The first gate is the forget gate. The second is your input gate I. The third is your CI gate, The fourth, sorry, this second is your input gate, third is the output gate, and then the CI is basically like more like a contextual information that is being saved. Then you have your previous context, that is CT minus 1 and HT minus 1. They both carry the C is the context vector, that is kind of like your memory state. HT is like your hidden state. And then you see that HT minus 1 interacts with your input and it gets involved with the forget gate, input gate, and output gate. And all of them send as an whatever output is being added to the context that is being built for this particular cell. And all these contexts then finally come out. CT and HT will come out, and your final output also will go up. So this is how you typically model the LSTM gate. And I just gave you the intuition. Each of these gates try to solve a different aspects to storing the information or extracting the most relevant information. GRU was an improvement over LSTM. What did it improve? They realized that LSTM is getting kind of expensive in terms of computation because there are three different gates and each gate has its own multiplications and everything. Instead, they realized, why don't we just combine two of the popular gates? So they basically said, okay, let's just have two gates, and the two gates is basically your output gate and your input gate. They kind of don't have any separate memory state or anything. So you see there is no C over here running. It's just HT minus 1. So they get rid of the context gate. So typically they got rid of one of the gates and the context that was traveling, and they now shared a lot of these gates with each other, like merged their usage. And at the same time, the context is also now being shared with the hidden state. So in this way, they were able to reduce the overall complexity. Now, if you go with this information, let's go back and see the answers. First is the number of gates. Like I just said, LSTM have three gates. GRU have reduced it by merging, combining memory into a hidden cell and having two states, two gates itself. Not combining. So basically, the GRU gates are called update gate and reset gate. So update gate and reset gate do the same thing what LSTM's forget output and input does. Is there that update and reset have much more simpler functionalities and hybrid functionalities. So number of gates is LSTM has three gates, GRUs have two gates. Memory cell, like I said, LSTM has an explicit memory cell, that C bar which was going. GRUs didn't have anything. GRUs share it, combined memory cell with the hidden state, and that is what is passing through as context. Now, gating mechanisms, LSTM, like I said, has three important gates: input gate, forget gate, and output gate. GRUs typically have, like I said, two, and those two are named update gate and reset gate. Same idea over here also. Update gate, like what do you think is update gate? We can think of it as, given the previous information coming in, how much should I update my current ones, and reset is how much should I forget that information. So that is what the update gate and reset gate will tell you. Complexity wise, of course, GRU's entire idea was to make it more efficient computationally. So they have come up with less number of gates. So that is why GRUs are less computationally expensive than LSTMs, because they have typically fewer gates. Okay. Any doubts or anything that is unclear in this particular problem? Then let's go to question 5. So this is your standard RNN's equations, hidden state equation and output equation. Based on the simple equations, and there are many matrices, two matrices, three matrices, my bad, WH, UH, and WI. Out of these three matrices, which of them are responsible for either vanishing or exploding gradients in RNNs? Think of it very clearly. How, when you're, what causes exploding vanishing gradients? Okay, and how is it affecting this RNN? Which matrix will particularly affect this RNN? Think of it very clearly. Try to understand when you're doing these partial differentiation, right? What are we doing partial differentiations? Yt is the output. So Yt doesn't necessarily contribute to your exploding gradients. Look at the right side of the equations. These out of these matrices, what will contribute? No, it's not WYHD. Okay. Uh, sure. DH3 by DH2, you're telling me is the operator, right? But in this particular, do your same DH3 by DH2. Just assume HT minus 1 to be 2 and HT to be 3. What is the matrix that is contributing? You're on the correct lines. Just tell me. It's just UH. It's not HT minus 1. So let's see. Okay, let's discuss how it actually happens. So this is your typical RNNs. So let me make it slow. Let's go step by step and look at the let's look at the equations of how these particular gradients come back. Forward pass is in black color, which is I think at this point very straightforward. You get your h0 from your previous time step. Each time step gets an input like this is x2, t2 minus 1, sorry, xt minus 2, xt minus 1, xt. And forward pass, you just calculate the corresponding. So theta over here, theta x is your weight matrices basically. This is, you can think of it this to be like wx, theta h to be your wh. Okay. Now the uh, difference that happens is basically when you're trying to you go to the forward pass, you calculate y, and then you get your output L. Now, when you're actually, what happens is when you try to back propagate, each of them will have partial gradients, right? That's what your entire back propagation does. So, to what do I mean by that? Let's say to identify if how much of LT depends on WX, we don't directly do, we'll write DLT by DWX, but we know that LT itself depends on a bunch of composite functions. So, it will be something like dlt divided by dy hat, which is the output, that is multiplied by dy hat by dht, which is further multiplied by dht by dwx. So this is your standard way to do a back propagation where you calculate partial gradients for each of the different terms that are being dependent on in between lt and wx. So that's what you actually see in these red color lines that is happening. So this is the red color. Let me highlight in different color. I'm highlighting in green. So these are all the partial gradients that are being calculated. Now, uh, so one small mistake I did over here. This is actually U. So now the question comes, out of all these equations, out of all these matrices that we're multiplying, when you do partial derivative, what happens? So if you go back to the equations which we had, so ht is calculated by wh of xt, uh of ht minus 1. Okay. So WH is nothing but the WX, which was there in the previous slide. That notation wise, you can, I think you can, this is like the WX, which I wrote previously. So that is nothing but the WH. Now, if I want to calculate with respect to the output depends, usually you calculate with respect to weights or biases and HT. Okay. So output is fine. There's not much of a things that can going on. Weight matrix is also something you're learning. There's no fixed matrix as such, which we have. If you look at this HT, this is where the gradient problem comes in. And if I do, so the two things which are learnable in this is either you do it with respect to dwh or you do this with respect to dht minus 1. Just like someone pointed out in the chat about how you want to do it with dh3 by dh3 with respect to dh2. That is what this particular partial derivative is. Now, what is this equation? Now what is this partial derivative? If you look at the equation, sigmoid value, the standard sigmoid differentiation, let's just call it sigma, sigmoid over here, sigmoid of h. That will happen. That is not a problem. That gets multiplied by the inner input of the sigma, which is there, right? This particular term. So let me write it over here. WH into xt plus UH into HT minus 1 plus BH. Now this inner term, if we differentiate with respect to HT minus 1, what will be left? UH. That's it. All rest of the terms will go out to 0 because they're not dependent on HT minus 1. So because of this, UH is now a matrix that is involved when you're getting the gradients. Now if UH is shrinking your outputs gradients, then extremely fast, then you kind of will have vanishing gradient problem. Now if UH will uh, expand your multiplications, when you're doing this multiplication, if it just enlarges them one after the other, then you have exploding gradient problem. So I hope this is where you're ending up with the problematic area of expanding and exploding and vanishing gradients. Is this clear? Any doubts? Or if you want me to repeat once again, I can definitely repeat. Okay, I hope this is clear. If not, please ask me. For now, I will move on to the next problem.
Sir, please repeat once more.
Yeah, sure. So here, when you see the forward pass is very clear, and here we have multiple UH and this WX is nothing but WH. So when you're calculating the backward propagation, you always start off from your last node output. Output is dependent on HT. HT is dependent on your WH with input. This is how the pattern goes. So when I typically want to differentiate with respect to WX, which is this theta x, I have to first differentiate with respect to Y hat t, differentiate with respect to HT, then come to differentiating with respect to, like this way basically. Come with differentiating with respect to WX. That is what I wrote over here. So this is typically how you do your standard backpropagation. Similarly, if you want to differentiate dLt with respect to du of h, I do the same thing. Let me make it in green otherwise. So if I want dl by duh, what do I do? From LT, I differentiate first with respect to y hat, and then from y hat, I'll have to differentiate with respect to h. Then I will end up with this particular UH. That's the only dependency that happens. You don't have to go down because here there is no UH, right? There is no UH here in the bottom. So you don't go down. You just have in these two steps. For here, you have these three steps. You HT, this, and another term for WX. So let's now see the equations that will pop out when we start doing this partial differentiation. So these are the two equations that we calculate with respect to HT and YT. So with respect to HT, you have two different types of partial derivatives that we can calculate. The first one is dou HT divided by dou WH. This is differentiating the HT equation with respect to the weight parameter H. Or the other option which we have, or which we will have to do, not option. The other partial derivative which we calculate is dou HT divided by dou HT minus. Now let's focus more on the second one. First one, because if you do first one also, nothing actually happens. You just end up with xt. So nothing interesting happens over here. The interesting happens in the second equation, second partial derivative. So when you do second partial derivative, now what is the equation? Let me clear this. Now what is the equation of ht? It is sigmoid of some input term. Okay. Sigmoid will have its own differentiation. So for example, sigma of x, if I remember it correctly, it was I think sigma into 1 minus sigma of something. This was sigma's differentiation. I'm not sure, something like this. So we're not concerned about this particular term, sigma's differentiation, because you get some value as an output. What we're concerned is this inner part which is there, now that is where the dependencies are. So how do we differentiate this linear equation which we have? WHXT plus UHHT minus 1 plus BH. Now we have to differentiate with respect to HT minus 1. In this linear equation of three terms, the only term that is dependent on HT minus 1 is the second. And what is the differentiation of the second term? There's only single HT minus 1, so that will get cancelled, and you're left with UH of t. So UH of t comes out. So this is how we used basically the chain rule along with the product, the multiplication rule of differentiation, and this is what you end up with: sigmoids whatever differentiation multiplied with UH. Now this matrix, if because there's a multiplication, it's a matrix vector multiplication of sorts. So what is a matrix vector multiplication? It just contracts and shrinks your input. So imagine UH can either contract this particular gradients which are of sigmoid and overall give an output which is much small value, or UH can make these gradients expand into a bigger value and the output gradients will be a very high value. So depending on UH property, your input and output, your output can either be small or your output can either be big. And if your output is small, you end up with vanishing gradient. Your output is big, you end up with exploding gradient. So that is why the only matrix in these equations that are typically responsible for vanishing exploding gradients is UH matrix. Is this clear now? Any doubts? Any further doubts?
Now that is clear. Thank you, sir.
Yeah, thank you. Okay, now let's go ahead. Now, if this is clear, very similar question. Here, it's more about the same matrix UH, which we just saw. And we are having certain properties of UH called the eigenvalues of UH. Okay, now based on this particular property of eigenvalues of UH being greater than 1, what is the potential issue that might arise? These are the four options. It's a single correct option. Pick the one which is correct. The correct answer, as posted, it is 2. So let's maybe see about think about what is happening. I think pretty much I answered in the last problem only. Let me revise what is happening. So sorry. So let me read the question first. The question is: consider an RNN being trained on a sequence data using backpropagation time, standard practice. Given that the particular matrix, recurrent matrix UH, has an eigenvalue greater than 1, what is the potential issue that it might arise during the training process? Now, firstly, before even going to the options, what does eigenvalue even greater than 1 mean? Okay, so what I was saying previously, all of these are matrix multiplications, right? Matrix vector multiplication. Let's say we always see this typical AX equals to Y. This is the most standard equation you're introduced to when you start linear algebra. What does this AX equal to Y even mean? Let's look at it more diagrammatically. So X is a vector. Let me put it in proper notations. Y is a vector. A is a matrix. Now this vector, let's say we are in 2 dimensions. A very simple case. Okay. In this 2 dimensions, X is somewhere over here. Now you have this matrix A. When you multiply with X, there are different ways this X can, what do you say, produce an output. What are the different possibilities it can do? This X can get big, X can get small, try to put it in smaller, or can also shift, translate, can go here or it can even go negative also. Doesn't have to be in positive directions. All of these are possible. To do any of these things, you typically multiply it with a matrix. That is what matrix vector multiplication means. It is transformation of your input vector into a different type of an output vector. That is what these matrix multiplications with a vector do. Now, if this particular matrix A has an eigenvalue of one greater than one, eigenvalues basically are something called as independent. So it identifies the dimensions which are in which the x will try to squeeze or shrink. So it's a entire theory. Let me try to give it in a more simpler terms. I don't want to get into the mathematics behind eigenvalues. Think of eigenvalues as it is like special type of directional vector directions along which says that along this particular direction, your input x which is there now, it will either get squeezed or it can either get expanded. So there are two things. Eigenvalues is the value itself. Then there is eigenvectors. These are the dimensions. So if eigenvalue is greater than 1, then typically along the corresponding eigenvector direction, x can get expanded. So what do I mean by that? Let's say, mm, so let's say some eigen direction. I think we'll need three dimensions to visualize this better. But okay, think of it like if you had this rectangle, input rectangle, and if you multiply it with a, and along one of the directions, the eigenvalue is greater than 1. So the output after multiplication, let's say this is the eigen direction, e.g. So along 1 it is greater than 1, so it will be like something like this. So you see along that EG direction, everything got stretched. The input vector gets stretched. So this is where this is what basically happens to your input when you have eigenvalues greater than 1. Opposite happens when it's less than 1, where your input vectors will get shrunk towards it, uh, shrunk after getting multiplied with a. Now, why is this all relevant? This is relevant because if you go back a few steps, this is what we had. We had a vector, we had multiplying with this particular UH. Now, if UH has greater than one value, that vector which is getting multiplied, that will get expanded. And once it gets expanded, then you're having, you're like enlarging the values, gradient values. And two big values multiplied with each other produces a bigger value. And at the end of the day, you end up with exploding gradient problem. If in this question, someone asked the same thing, but instead they said eigenvalues less than 1, then it would be the vanishing gradient problem, where now all the vectors will kind of get shrunk and all the gradients will kind of get shrunk, and then it will be like two small values multiplied with each other becomes a smaller value, and overall it will be a vanishing gradient problem. So yeah, I hope this is clear. Any doubts? Anything you want me to repeat or anything unclear? Okay, great. So if these are all clear, then any other something unclear in the any other problem, because we'll go to the second half of the live session, which is a code walkthrough. If anything about the numericals is unclear, I can repeat. Otherwise, we can move to the second half. Okay. So in the last coding practice, code walkthroughs, we discussed about your standard segmentation algorithm. We also discussed about actually object detection algorithm on how you can typically deploy your standard YOLO algorithms like YOLO 5 and YOLO V5 and YOLO V7 using their existing repositories. Now, today we will move towards recurrent networks, right? And same, pretty much everything follows the same. The way you created your neural network class itself, or the way we pre-process your input data, or the libraries which we use, and also the for loop which we write for training, all of them remain the same. Nothing really changes. Even if you're shifting the algorithm, theoretically, there's a lot of shift between going from CNN algorithms to RNN algorithms. Code wise, There's not much of a difference. Everything remains same. It's just that subtle few things when you're writing or creating your algorithm or network, you need to make sure you are doing it properly because it's a slightly different algorithm. So let's discuss that today. So the problem we're trying to solve is a character to character modeling. So what do I mean by that? Let's say I have this sentence, this particular text, hey, how are you? And typically after hey, how are you, what is the next type of a character I can expect? So character is nothing but letter. So in this, you have like H-E-Y, hey. This will have three characters. Similarly, H-O-W, how, will have certain number of characters, three. A-R-E, three. Y-U-Y, three. And the spaces in between them are also characters. Those are like white spaces, correct? So in this particular state sentence or sequence, you have, I think, 3 plus 3 plus 3, 12. Again, 3, 3, 3, 13, 15. 15 characters you have in this hey, how are you sequence. So, what we're trying to do over here is after hey, how are you, what should be the next character that should come as an output? Ideally, we would say white space, right? Because, or it could be not just white space, it should be question mark also, if that is a possibility, depending on how what is your uh, dictionary size and everything. But yeah. Okay, so given these particular characters, we want to identify. Let me show how. So this is what typically we have. Like if I have the input sequence like hey, how are, instead of you, I'm just giving yo. Now what I want my model to give as an output is you, because that will complete this word you. So that is why the target is now you. Similarly, if I'm saying good, I am fine, there's nothing as an output. Fine is completed. So you just put you don't output anything. Ideally, there's a white space here. We are not having a white space in the target. Similarly, have a nice day. That y will be now predicted by the neural network model. So this is the problem called as character level modeling or character to character modeling, whatever you want to call it. Is the problem statement clear? What we're trying to achieve? Is there any doubt in this? Okay. If the problem statement is clear, let's go and start looking at the code. So as usual, as always, I always encourage and would suggest import all the necessary libraries in the start, which will definitely help you with your. It's just a good coding practice. So here we first import PyTorch as torch. We import the NN module in PyTorch, which is the neural network module, and we also import NumPy as NP. Now we, let's say we have these typical three sentences. So just to see how the sentences are. So let's say we want to first join all the in each sentence, right? We want to join all of the words together. That's what we do with join.text, and it extracts all the unique characters from all these joined sequences. Why do we need unique characters? Because there are a lot of repetitive, right? You can't say that each character to give a separate like a unique word. You need to first identify what is the vocabulary of your entire data set. So when I say vocabulary, okay, let's think about it this way. In English, there is only a finite number of words. And how do you find these finite number of words? You open a dictionary and you go to a dictionary, you identify what are the each words, and this is what the meaning is. So that is what we're basically saying in this particular creating a dictionary. You first identify what are all the unique characters in your entire data set. Our data set just has three sentences. It is not big. In these three sentences, identify what are all the unique characters present because we're doing character level modeling, and then convert all of these characters to numbers. Why numbers? Because computers can only deal with numbers. It has no like the letters have no meaning. It only deals with numbers. So that is what we're basically doing. We first join all these sentences together. Then we convert them into integers, and this will become a dictionary. So now if anyone wants to identify what are all the possible characters present in this particular simple three sentences data set, they can look into this int to character dictionary and they'll get to know. So if I print it, this is what the dictionary looks like. I corresponds to 0, A corresponds to 1, H 2, and so on. So there are in total, I think, sorry, yeah, I think there are in total around 15, yeah, 16 different, sorry, 17 different factors we have. That is the length of a dictionary, 17 different characters. As usual, please stop me if something is not clear, something, because this is not vision. If you remember, this is just easily going into text, so things might not be very clear. Please ask me if something is not clear. Again, this is only for understanding. Again, to we move back from here to images very soon. It's just for your understanding of how to use these sequence type of things in images, because videos are typically sequences. If you think about video, it is nothing but a bunch of different frames, right? So videos are nothing but your sequences. So that is why we are trying to first understand sequence level modeling. Then from there we will go into more complex videos, or in other, you'll also see other tasks also. So please stop me at any point if this is not clear. Yeah. So we print what is the longest string. The longest string. What is a string meaning? String meaning the sequence. Out of these three sequences, what is the longest sequence? What do I mean by long? Which has the most characters, and which has the most characters, which is 15 is the highest characters which we have. So that is what we're just finding out. Now next what we do is, each particular sequence which we get, they're typically not of the same size. Like for example, hey, how are you? Good, I'm fine. Have a nice day. These are three different sentences. Each sentence will have different number of characters. They don't have to necessarily have the same number of characters. So now there is a mismatch between different input sequences that we have. Now, typically this is bad for the model because it would prefer a standard matrix or tensor size to go as an input. If the tensor size, if each sentence has a different size, the tensor can't be formed because it will throw an error. It says that your sequence 2 is of size 14, sequence 1 is of size 15. You can't combine them to make one tensor or matrix, whatever you want to call it. So typically, we want all the sentences to be of the same size. How do we do that? We do that with padding. Just like if you remember in convolution, also we had padding. That means you're either adding some extra values at the border of your image, right? Typically, here also we do padding. We can do end of the sentence padding, start of the sentence padding, or both paddings you can do. You can either do any values. You can, here in this particular case, I'm just adding white space. Again, not necessarily to stick with white spaces. You can add any particular character and we can call it a padding character. But you have to be consistent with that. And it should not, interact with other characters in your data set. It should be in such a way that it's a unique character only, uh, what is it, used for padding. It is not used for any other element in your training. Then only it makes sense. Otherwise, the model will get confused. In this case, white space is used as a padding sentence. Padding element. So how do we do that? We basically loop through our data set, which is three sentences. And for each sentence, we check if it is less than the maximum length, which is 15. If it is less, you just add white spaces after at the end. So that is what has happened. Now we create the inputs and targets. This is like our X and Y's which we have in a data set, right? Typically, that is what we're creating. So for each sentence, you basically input sentence will remove the last character because we want to predict some character, right? So we are removing the last character. Now for the target also, we are removing the first character. Now why is this happening? Because the target is character level modeling. So if it is H as an input, what should be the next prediction from the model? We want E. That is why E is the target for H. So for E, what is the target? Y. So if input is at E, the output will be Y. That is what the actual output will be. Similarly, for Y, the target will be a white space. Now for white space as input, the target will be H. I hope you're understanding why the target is shifted one step towards the right. Because target means what should be the next character that should be predicted. One input is what is the given particular input, what should the model predict as next. So if given is H, we want the target to be E because that is what we want the next character to be predicted as. So the target is slightly shifted towards one space to the right. That is what is happening. And that is where you end up with this U, which you finally want to predict from your input given sequence. Any doubt in how we are modeling this? Why is there a shift happening between the input sequence, target sequence, or do you want me to repeat it again? Okay, great. So we just create these the data set. which is three simple sentences. Each input has its corresponding target. How do we do that? Just like I said, for loop we have three times we run it. Input sequence, just remove the last letter. Target sequence, remove the first letter, and remaining all keep it same. That is your input target pair. Now, once you have characters, next thing you have to do is convert it into integers. Like I said, my algorithm only understands numbers. So that is what we're doing. Each input sequence you're converting into this dictionary, using this dictionary character to int into a integer. Similarly, target also, the dictionary which you just created above, we use that to convert these characters into numbers. Now, once you do that, you need to create a particular one hot encoding for each of the input, for each of the output, sorry, target integer that you have. Saying that, okay, out of all the possible values in the dictionary, which one is the which particular character should most probability that is be one. That is for ground truth, it will be one, and the remaining all will be zero. Your standard one hot encoding, which you do in classification also, right? Classification, what we do, labels are numbers. Let's say like there are five classes. What do we say? Numbers should be 0 to 4. We give it as numbers, but actually in the PyTorch in the backend, one hot encoding happens to the vector y. What does one hot encoding says? When you have like five class problem, you create a matrix of 5 cross 5. Okay. Sorry, not matrix. You create a vector of dimension 5, and whichever integer is your actual ground truth, that particular index in that vector corresponding to that integer, that will have 1. Remaining all will have 0 values. So that is why it's called a one hot encoding vector, because it is a vector where only one value will be 1 and remaining all values will be 0. And where it will be 1, that is your actual ground truth class label itself. So same concept we are doing here also. So here we're doing it by hand, but typically PyTorch can also take care of it. So here we're creating those particular relevant character, sorry, uh, output one hot encoding vectors. Now let's go to the same one hot encoding vectors converted to an input sequence also. This is how the batch now looks like. Initially we had 3, 14, 17. Now after one hot encoding, you have batch size. In this it's a simple, so we'll keep it 3 only, nothing big of a batch size. Sequence length and the one hot encoding size. This will be typically your one hot encoding size. I think it should be, we didn't print it. You can just run this code and you can see what exact value you get at the one hot encoding size. Oh, sorry, my bad. Your one hot encoding size is 17 over here. Your sequence length is 14 and your batch size is 3. So this is your input shape now converted to these this particular tensor 3, 14, 17. Okay. Now all of these are basically still numpys. Okay, none of these are actually tensors, and I always say that PyTorch will only work with tensors. It won't work with NumPy arrays. So it is very important that you convert all of them into PyTorch tensors, and that is what we're doing. Input sequence converted from NumPy array to tensor. Target sequence also we're converting to tensors. So once you do that, now let's actually devise a RNN architecture, which is very simple. So up till now, again, what I said till now, these are all NLP related tasks of creating your data set and everything. Even if it's not clear, it's fine. What we're doing next, that is most important, because that is the model which we will use even in images. So make sure you understand now, from now on, whatever I'm saying, even up till now, if it's a little bit not unclear, it's still okay. You can look at it on your own. Okay. Now, before creating the model, this is a helper thing which we always say to look for is check if CUDA is available. So this command in PyTorch helps you do that. Torch.CUDA is available. It will return true if you have a GPU. It will return false if you don't have a GPU. It's always important to be connected with a GPU. Like you can see where in Colab by default, when you run this notebook, it will be T4 connected. Because without GPU, it will take weeks, months, sometimes to train networks. So it's always important to do that. And this is just a print statement. Like if it is true, the CUDA, you just print whatever device is available. Torch that device will tell you what is that device. And so it will store the device name, and we are printing GPUs available. If it's not, we just say GPU is not available. Now let's create a model. This is a simple RNN module, nothing fancy is going on. And we do the same way which we do like CNN architectures only. We first create a class name called model. This model will inherit the parent class nn.module. This is very important. If you don't do this, PyTorch will not know that this class what you created is a neural network type of a class. This nn.module will tell to the PyTorch this is a neural network class. In typical neural network class, as always, we have two functions that you have to worry about: init function, forward function. There are others also, backward and all, but typically you don't deal with it unless you come with your own backward passes, how to do it and everything. But other than that, these are the only two functions which you always interact with, or you have to customize it. Init function, what does it do? Init function basically creates the global variables like number of layers, size of the hidden dimensions, and yeah, any other global variable which you will be needing for your neural network. All of these are created with inside the init function. So here, what are we creating? We're creating the number of hidden dimensions, number of layers we want. Uh, just a minute. Just give me a minute. I'm sorry. Yeah. So coming back, we were basically first talking about what are the RNN init function should have the values. First is the hidden dimensions. Then we talk about how many number of layers we need. And here is your RNN neural network created for you, or the default neural network which is present in PyTorch. You can easily access it like nn.rnn. Just like how you did nn.conv2d, right, for convolution. Similarly, you can just do nn.rnn, and this will take care of all your, that matrix vector multiplication between input and weights and the hidden states and everything. That will be taken care of. And then finally, a fully connected linear layer to predict your output. From output needs to be predicted, right? And that will be done by a fully linear layer, which is a fully connected layer. In the forward function, we basically try to tell what should be the data flow. What do you mean by data flow? Like what should be the input, given the input X, where should it go to which layer, and from the output of that one layer, where should it go to the second layer, and etc. So here we first do the same thing. We identify, this is just to variable notation, what is the batch size. Then we initialize the hidden states. Typically, you can write it by default, or here we use another function called init hidden. You don't have to do it. You can do the default init hidden function which is there. But if you want to initialize in your own manner, since we want to initialize with zeros, we override that function and write our own function init hidden, and where this is all zero function. Okay, self.init hidden will basically make sure all the layers are initialized to zero. Now this hidden states will go as an input to self.rnn along with your input x, and you get two values: the final hidden state and the output state. And then we reshape this output into a particular into a vector. It's just like how you do pooling, right? Global average pooling, or flatten your CNN output into a vector. Similar, think of it to be similar in that way. You're basically you're reshaping your output of your RNN so that it will be compatible to send it as an input to your fully connected network. And then finally, your final output, which is in predicted, or that last layer, right? Like the logit layer or the softmax layer that will come as an output. I'm sorry, logit layer, softmax doesn't come out. So the logit layer which we get, that is the output over here, which we're returning. If you want, you can also return the last hidden state, because sometimes you want to use it for some analysis and etc. Otherwise, you can typically just return the logit layer itself, which is the output. and that's it. You created your RNN architecture. And then we just first call this class model which you just created. You give all the input arguments which we defined, like what should be the dictionary size, what should be the output dictionary size, output size, which is again the dictionary size itself, number of what should be the size of the hidden dimension, and number of hidden layers. Then you send it to the device. Here model.device basically sends it either a GPU or a CPU, depending on what the device is. Like I always said, make sure it's a GPU. You define how many epochs you want to train, 100 epochs. Define the number of learning rates, which sorry, not define the learning rate, very simple, 0.01. Then we define the loss function. Again, simple loss function, cross entropy loss, which is already existing in PyTorch. You don't have to worry about it. And then you can you have to create the optimizer, which is your Atom optimizer. And our Atom optimizer again takes into things as input. One is your which parameters should it optimize. So optimizer is basically update, right? The gradient descent, weight update, and all those things happen. So it needs as an input what is that parameters that it has to update. And also it takes as learning rate, because if you remember in the gradient equation, gradient descent update equation, we have the gradients multiplied with alpha or eta value, right? That is the learning rate. So that is why it needs learning rate as an input. So once you define all these, this is a simple training loop which we create. Here, since we don't have a very big data set, it's a small data set, we're not doing batch training or anything. We're not doing mini batch gradient update or anything. We're just doing like batch gradient update. Like update the model after looking at the entire data set, because it's a small data set. But typically in the other classes, like we saw, you will always have to do a mini batch gradient when your data set is big. It means you'll have two for loops. Since our data set is small, it's just one for loop. Okay. So inside that epoch for loop, first thing we do is clear out the previous gradients. That is what optimizer.zeroGrad does. It basically makes sure that there are no what do you call it, ghost gradients or unwanted gradients which are coming from the previous model. Because if you don't put this line, sometimes that gradients will interact with your current gradient model updates, and then your model will get very wrongly updated and your accuracy will go, or performance will be very bad. So make sure you always have this line written before you do your model update, current time steps model update. Try to remove it and check how bad or how fluctuating your model performance will get. So after that, you then send your input sequence as like your input sequence. You send it as an input to the model, and the we saw that model architecture outputs two things: the output, which is the final logic layer, and the last hidden state. Now we get the send the output to device also. Not needed actually, but you can always send it. This because it's taken care of when you send model to device only. Then we send target sequence. This is the actual target value label, right? That you need to send it to device because it has not been sent yet. Finally, we calculate the loss, which is the cross entropy loss between outputs and targets. And here is the back propagation. Loss dot backwards basically calculates all the partial gradients which you need for during your back prop. Optimizer dot step will update all the weights according to the partial gradients which will calculate. And after every 10 epochs is just a printing statement to check how the loss is varying after every epoch. So we have for 100 epochs, and the loss starts off from 2.4 and comes to 0.13. Now let's come to another. This is now again helper function of sorts to see how the predictions look like. Because if you remember what we did to characters, which is human understandable, converted them into numbers, sent those numbers to model is trained on those numbers, and now model can predict those numbers. But those predictions are still in numbers format, integer formats. If you look at those integers, we won't understand what those are. It's understandable to the model, but not to us. So we have to again convert those integers back to characters. So that is what we're doing in this predict function. So you take your input character, that is like your test character, test example, you convert that first into integer, that input test example. Then you convert it into one hot encoding. Then you send it to the model. The model's output, you then calculate the softmax of on top of these logics to get which is the more right probability prediction character. Like there are like 17 characters, right? Out of the 17 characters, which particular character has the highest probability that you will get once you convert them into softmax. So from this prob vector, you identify the max prob, and that will be your predicted character. Now this character predicted character is converted back to uh, so yeah, it converts back to your character value. This is an integer, it converts back to your character, and that is what you can see over here. So this is another sample function. This it's basically tries to figure out, sample is like the overall test inference loop which we have. So it first creates model in it first instance sets model into eval state, and then it will have the word hey. Hey is that sentence which you are giving. Hey, it converts all of them into lower cases, then basically uh, converts sends each of them into the predict function, that particular each character, and then you output the characters, and what you're getting as an answer, good, I am fine. So 15 basically says what should be the output size that I want the model to keep on predicting. So 15 characters next I want to predict after good. So if good is coming as an input, I want next 15 characters to be printed after good. So each, like GOOD good, each of them will go as an input to the model, and the predicted, well, after good, whatever is getting predicted, that will again go as an input to predict for the next character. But like that, you will have to do 15 times. So that is what this 15 corresponds to. So if you give good as an input, the output I'm getting is good, I am fine. So with just three simple sentences and a small RNN, the model is actually able to understand this and give this as an output, which is not bad. Good I'm fine is exactly what any human would reply after if you're giving good, right? Good I'm fine is a very high probability sentence. It's not a bad sentence. So this is it for RNNs. Any doubts in RNNs, or should I move to LSTM's GRUs? Again, everything remains the same. It's just the architecture we have to slightly create it differently, but the logic training steps all remain the same. So it's very important. Is everything clear? Anything, any doubts or anything that I have to explain again? Okay, great. If it's all clear, let's go to LSTMs and GRUs. Yeah. So here, of course, LSTMs and GRUs is a slightly bigger models, and we already showed that even with a simple RNN, we were able to solve the data set. Now we try to go with an actual one of the real world type of data set where we predict what is the consumption, electric consumption uh, uh, of a particular given location. Basically, this is the data set AEP hourly. This will tell us how much electricity has been consumed in for every hour in terms of watts, megawatts, basically. So here, what is the sequence? So typically, you look at your history like in every hour, right? So like you look at the last 10 hours and you identify, okay, how much will be the consumption of electricity for the next few hours based on the history of consumption. So this is a sequence modeling. It's like you can also think of it like a share market. Everyone is aware about your stocks and share market, right? So you typically look at the past history trends to predict how the future will be. Same thing, even think about like electricity consumption. You look at the history like a certain window period of time based on which you can predict how much electricity will be consumed in the next few hours. So same type of modeling we are trying to solve over here with GSTMs and GRUs and LSTMs. As always, first things you import necessary libraries. Since it's a bigger, we want to visualize and everything, we import some helper libraries like pandas, numpy, pandas, matplotlib, and sklearn and preprocessor. So we first load this dataset. It's available over here. You just have to follow these commands. You'll download the dataset from this particular URL link which is present. So this is how the dataset looks like. You have the date and time stamps and the consumption of electricity in terms of megawatts for each of these date and particular time. Now let's convert this CSV data into the particular data format which you want. What?
So this URL link will be provided.
Yeah. So this URL is open source basically. The what you see raw.github content. This all is available on. You can just have So this particular URL link, append it with AEP our CSV file. You'll get it online. It's an open source data set.
Okay.
Yeah. So we convert this particular data into the data format which we want. Now, what do we ideally want? See, if you give something like this, 2004, I think this is like 31st December 2004 at 1 a.m. This 13,000 watts has been consumed, megawatts have been consumed. But giving a module this particular format of date and time of 2004 12 31, that might be slightly hard for the model to understand. So we have to be smart over here. So whenever you're given a data set, don't just directly use whatever they are giving, like these columns which we call features, right? You don't have to directly use the features which the data set is giving. You can maybe make some, better features out of the features which they are giving. Now, what do I mean by that? Let's say this 2004 12 31, that might not be very easy to understand for a model. What is easy to understand for the model is if you break this particular date, right, 2004 December 31st, into three different columns: year, month, and day. Then it will be like even more simpler task for the model to find patterns across these features. So at the end of the day, it's all about pattern matching, right? Understand pattern recognition. So if your features which are corresponding to these patterns are already complicated and not easy to understand, it will take model a lot of time to understand what are the patterns. But if a human, the domain expert, is intervening and giving the data set in a much more clear format or simpler format, it will be easy for the model to understand. So that is exactly what you do in this particular code. You create all these new features from that existing data set which we are given. You identify what is the hour, what is the day of the week, what is the month of the week, what is the day of the year. Okay, so this is how you typically create new features based on the features you have. And then after that, you do something called a scaling of the input data. This I've touched upon in the starting lectures, but let me come back to it again. Why is this important? I always say that whenever you have any features for your machine learning model, features are nothing but these columns, right? You just created three more columns: hour, day, and everything. We typically want each of these columns to be in the same range. Like 0 to 1 is the most standard range, but you want typically these features to be in the same range. Why? Because when the model learns on absolute numbers. So, for example, years can go from 2004, let's say we're starting from 1900s. It goes from 1900s to 3000s. Okay, that is the year range. But hours, and for that reason, can only go between 1 to 24. That is the only number of hours we have in a day, right? Not more than that. So you see the range of years and hours are very different. Years can go from 1900 to 3000. Hours can only go from 1 to 24. Now, for a model, a number is a number. At the end of the day, it's an absolute number. It doesn't understand. Oh, it's a year, right? So 1900 is the first starting of the year. It doesn't see that way. It sees 1900 as an absolute number, and it will always say, okay, 1900 for years is relatively greater than 24 as hours. But if you actually look the meaning behind what we just created, 24 is the max value of year, whereas 1900 is the least value max value of an hour, whereas 1900 is the least value for an year. So we ideally can't say that 1900 is greater than 24 in that, semantic intuition. So if you're converting all of them to 0 to 1 scale, then 1900 will become 0 in the years column, 24 will be 1 in the hour column. So that is why we always need to convert all these features into same range, so that the relative importance, ordering, everything will stay correct. Otherwise, there will be a problem for the model to learn. Is this clear why we scale the data? Any doubts? Do you want me to explain that again? Okay, great. So that is what we do the scaling over here. We are doing min-max scaling. There are several types of ways to scale the data. Normalization. You can normalize using Gaussian distribution. Min-max is one, and etc. So once you do that, you try to get some you labels basically now. So let's for that for getting the labels, you need to first look at a window because it's a sequence problem, right? So here we're looking at a period of 90 points basically. So the 90 is the loop back window where you first look at all the 90 points till now, and then you predict the next value based on these 90. So that is what we're doing. The inputs are labels. We are basically creating a look back window. Each input will look at 90 values, and the labels will be one value, which based on that 90 values, you predict one value that will be in the labels. So that is what these inputs and label correspond to. You just write a for loop, and you from this Excel sheet, you always check. Like for example, for one, there will not be 90 values. Whatever values are available, zero, right? That will only be there. Similarly, for 90th value, all these first 90 values will be in the input, and then the 91st value, not 91st value, 90, whatever value after 90 will be then, that should be predicted as a label for the 91st value. So that is what we're basically doing over here. In this for loop, we're trying to create that window, and then keeping in that window whatever value comes in that window, that will become input. The next value after that window will become the output label. Then you then split whatever data set you just create into test and train. Here we are simple standard test and train, like 10% test, 90% train. We're not doing validation all. We have to do it, but since it's a toy example, you we are not doing it here. But you, when you're creating your own models, always create the validation set. Okay. Now let's create the data set. You use the standard tensor data set class. Whatever data set which you just create, train and test, you create the train data set. Data loader, we all are aware till now. What is a data loader? It will basically create your mini batches that is useful for your mini batch gradient descent. That is what the data loader is. And then you have your check function, whether you're running on GPU. And now you create your GRU network. Simple, what is a network? You create GRU net, inherit the NN module class. Then in the init function, you create what are the important variables, what are the hidden dimensions, number of layers, and just simply like instead of nn.rnn, you have nn.gru. And then you create a linear function. Even in the forward pass, very similar. You take x, send it as an input to GRU, and then you send that output of GRU to the fully connected network, and then the fully connected network will give you the logit as an output, which is out, and this out is returned. It also returns the final hidden state. Same thing for LSTM also. Only difference is instead of nn.gru, you do nn.lstm. Everything else remains the same. That's it. So once you're able to create that, the training loop also remains typically the same. Here we have created a train function which we'll call later, but the function remains the same. It will first identify what are the network you want to create, whether you want to create GRU or LSTM. It defines the loss, which is mean square loss, Adam optimizer, and then it starts the training. Here we are doing mini batch, right? That's why we have two for loops: epoch for loop, batch for loop, and then in the each mini batch we send the input x, we send it to the model, get the output, calculate the loss, do loss dot backwards, and then optimize the dot step. Make sure you always do that zero gradient here. We're doing that. Make sure you always do that also. These are the typical 4 steps, and this is done for each mini batch. And then you, after all the mini batches are completed, we say one epoch is completed, then you do for a number of epochs whatever is given. Then you do some print statements just to keep track of the loss functions. Evaluate function also, you do the same thing. You append the outputs, the targets, and then you calculate the particular performance. Here we use something called as SMAP. So SMAP stands for symmetric mean absolute percentage errors. I think, yeah, that is the full form. So think of it like a very simple way to calculate like your standard MSC, right? Your standard error, what do you calculate? What is, how different is the actual value from the predicted value? This is what this is. Outputs minus target. How different is outputs, the predicted value, from the ground truth targets? But this is not very stable. To make it stable, you divide it with more different values with the actual targets and outputs to make it more. It's kind of like normalizing of sorts and make it more stable. So it comes off like to a proportion kind of a thing. So don't worry if you don't understand. It's not a very popular metric for us in computer vision. It's a metric when you usually do more sequence modeling. So anyone interested can look into it, or you can discuss. We can discuss later. But if you're not understanding this, don't worry. That is not a requirement at this point. Just remember there is a metric. You can replace this metric with your accuracy metric also. Doesn't matter. Just remember that you'll need some metric to evaluate your function. Okay. And then we typically train the GRU. We training. We just call the train function. You send in the parameters. This is the training how it's done. Similarly for LSTM also, we comment it. You can uncomment and check. So you check what is the evaluation. This is the metric 0.30.
Hello, I have a question here.
Yeah. Yeah.
How different is this SMAP as compared to accuracy metric?
Oh, these are very different. Accuracy metric. So it's like accuracy metric is done usually for more discrete kind of a things. These SMAP and MSE, right? These are done for more continuous values as an output. So it's the same difference between classification and regression, right? So classification typically has these accuracy metrics because you know that out of these particular classes you belong to one. For the regression, it could be any continuous value. There's no one class that you can attribute. So accuracy will not make sense over there,
Okay,
right? Yeah. Yeah.
thank you.
Okay. Yeah, so SMAP is again over here. These are the values. So this is what I wanted to discuss for in today's live session. Any doubts, anything that is unclear, yeah, I can answer right now. If it's all clear, then we can end today's session.
This notebook is available in the Excel sheet, right?
Yeah, the drive link. Yeah, yeah. S is symmetric. So if you look at this, so what you wrote, right? MAPE over there in the denominator, it is just divided by targets of I. That's it. You don't have these extra terms plus outputs plus. So what happens over here if it's outputs minus targets divided by targets? This is a proportion, right? So how much of the proportion of error is being calculated over here? So ideally, if it's zero, it means all of the output and target is very close by each other. So this is like a proportion, and you just divide by targets. But that is again was not stable, so people said, "Ki, let's make it more symmetric and stable," and then that is where they added the plus outputs and again divided that also by 2. So that is where the S term comes in.
How can I compare this with transformer architecture? Because
Uh,
sequential.
yeah. So transformers is an entire lecture in itself. That is what week 8 is completely. So it's talking entirely about,
For understanding purpose, the key pointer.
yeah. So there are 3 points, not 3 points. I think there were like few points. The main important point is in RNNs, what we did was we were sequentially looking at the data. Like if your input had 4 words, you look at word 1, then do look at word 2, word 3, word 4. It's in a sequential manner. Whereas in attention, which is the building block of transformers, you look at the entire word at once and then you try to relate, okay, first word, how is it related to the fourth word? Second word, how is it related to the all the other words, not just fourth, all the other words. So second word will look at the first word and all the other words. So you see there's a parallel processing that is happening. So that is the biggest, one of the biggest speed ups or performance gains that we get when you do attention level modeling and your standard RN level modeling. Apart from that, there are other advantages like vanishing gradient problem goes away, long-term dependency problem goes away, all because of the way you're modeling the relationship between your words, or in this case, tokens or whatever you want to call it.
Okay, so compute required is more transformers, but if I need
Yes.
picture, I can definitely use RNNs.
Yes. So RNNs is still at, important to use if your task is not very complicated and if it can be solved with a limited, long term context window and everything. RNN, I think it's still relatively less complex, but transformers nowadays, people have invested so much time and made it faster. Ideally, the original transformers which came up, they were not very fast, but nowadays there are a lot of techniques that came up which made it fast, like sparse attention came up, and other techniques which have come up which makes it faster.
Okay, so can I have one model like RNN model and lightweight transform version, which will be executed in the same time slot? Maybe more or less it may be same.
As I see, that depends on what transformer are what is technique are you using to make it faster. You can always see this all depends on your exact task and everything. There's no like in any problem, right? In machine learning or deep learning, you don't just pick one model and stick with it. You take a few
The thing is, I want to understand, is there any lightweight version of transform?
Yeah, that's what I'm saying. Yes. There are techniques which make transformer faster. Like I said, sparse attention is one technique. Flash attention on a hardware level makes transformer training faster. So there are a lot of techniques which are available which you can use with the existing transformers. But there's I can't give you sure shortcut that will always be better compared to RNNs or in terms of compute. It can be that in your use case, maybe RNNs are doing much better than that particular transformer, even after using Lightweight.
Okay.
Yeah.
In terms of accuracy, I mean, MAP or whichever metric. So, is there any other metric that we use other than MAP? Yeah. Or
Yeah. Yeah, so sequential learning can use any type of so MAP is just this SMAP is one metric. You can use depending again on the task which you're trying to solve. Even your standard these stock markets and all those things, you can I think there's some I'm not getting the names for those metrics. That's actually not my field also, but there are other metrics that you can solve like SMAP and other type of metrics for sequence modeling. No, video frames you can use your standard matrix like accuracy and all. That because video
it's a sequential.
no. So you're okay, I think there's a confusion. This metric is not for sequence problem. This metric is for the continuous sequence problem. So here the data is in a continuous manner. It's not a it's the data. So this is a regression type of continuous output. This is not a discrete output. Now for videos, the output, like if it's a video classification, you take the entire video, which is a sequence model, which is a sequential data. The output will be still discrete. It could be whether it's a movie video, whether it's a game video, whether it's a other type of video. So you're getting the difference. The output matters over here. Output is discrete or continuous. The metrics change based on that, not your input. Any other questions? Any other doubts? Okay, then. Thank you all for attending. Let me stop the recording.